So we have our warm-up. So our warm-up is we want to find the missing side of these two triangles, but we want to leave it in simplest radical form. So we don't want to round and get like a 7.07 something, some weird irrational number. We want to try to keep it in that simplest radical form. So we're going to have to take that square root and we're going to have to break it down like what we were practicing yesterday. So just to start us off, looking at this, what formula can we use to find missing sides of these triangles?
Pythagorean theorem.
How does the Pythagorean theorem go?
A squared plus b squared plus c squared.
And what type of triangles can we use this for?
Right triangles.
Only right triangles. And which of those letters is important? Which of those letters is different from the others?
C.
C. What's important about C?
C is your hypotenuse.
It's your hypotenuse. It's that longest side. So, which is our longest side on our triangles we have up here? X. So if we were to fill this in, how would you fill in this formula? What would it look like?
5 squared plus 5 squared equals x.
5 squared plus 5 squared equals x squared. What's 5 squared? 25. So that gives us 25 plus 25 equals x squared. 25 plus 25? 50. So we have 50 equals x squared. How can we get x by itself? What do we need to do to get rid of that square? Square root. So we take the square root of this. We have to take the square root of 50. But once again, we can easily put in there a calculator and give us like 7.07 something. But we don't want that number. We want what the actual value is. We want to figure out what the exact square is. So we're going to take 50 and we're going to try to simplify it. We're going to break it down. So what are two numbers I'll multiply to get 50? 5 and 10. Okay, if we break either of these numbers down farther? 10. Okay, what can we break that down into? 5 and 2. So 5 and 2, we can't break those down farther. Do we have any pairs?
Yes, pair of 5.
Pair of 5. So you can take one or take a pair, cross it out. Now what happens to that other number? Is it going to go inside my answer or outside my answer?
Inside.
It's going to actually go outside
Wait, which one?
the 5.
Okay, yeah, I think two.
Oh, I'm sorry. Okay, that's my fault. So we get x equals 5 radical 2. Are we okay with this? Okay, cool. So 5 radical 2, that's going to be our x for that problem. So see if you can do this exact same thing. Set up your Pythagorean theorem, fill in your answers, see if you can solve for that other missing side we have on our second trial. Take a couple moments to do that. So what did we find for our solution?
7 radical 2.
7 radical 2. Okay, good. Now, looking at these two triangles, what do you notice?
They look the same, they have the same degrees.
So they both have 45, 90 degrees.
But their side lengths are different.
Their side lengths are different. Okay, so one has 5 radical 2, and one has 7. Yeah, some sort of pattern going on. Well, hold on to that. Put that in the back of your mind. Don't let it slip away. We're going to look at another set of triangles. So we have these two triangles. We have two side lengths. We're looking for that missing side length. So setting up this first one, what is if I use my a squared plus b squared equals c squared, what's my longest side of my triangle?
6.
6. It's opposite of my 90 degrees, so it's going to be my hypotenuse. So I know 6 squared is going to be my c. Doesn't matter which one's a and b, so one's going to be 3 squared, one's going to be x squared. What is 3 squared? 9, okay. So 9 plus x squared, I can't figure that out yet. That equals 6 squared, which is
36.
Good. Okay, so 9 plus x squared equals 36. How can I get that x by itself? What do I need to do? I need to get rid of that 9. So we'll subtract 9 to the other side. I'll cancel our 9s out. 36 minus 9, what will that leave us with? 27. Okay. Last step from here?
Square root.
Square root. We need to get rid of that square. So we need square root, cancel that square out. But that means I need to take the square root of 27. Square root of 27 is not something we know off the top of our head. So we're going to have to break that down. So I'm going to roll back up to the top to do it up here. Square root of 27. What are two numbers I multiply to get 27?
9 and 3.
9 and 3. Okay.
9.
And 9 can go into 3 and 3. Do we have any pairs?
3 and 3.
Okay, 3's. Cancel one out. So we have 3 on the outside, and then we have 1 3 that's left over. So x equals 3 radical. Good. All right, once again, same thing. See if you can get the second one. See if you can find where that other missing side is. Okay. What did we end up with for x on this problem?
5 radical 3.
5 radical 3. So we had to take the square root of 75, which is split up into 3 and 25, and 25 splits up into 5 and 5, however, what way you did it. We should get 5 radical 3. So once again, we have a set of triangles here. What do you notice is happening with both of these triangles? What are some patterns you see?
The side lengths are like the same number multiplied by 2 is the different number.
So that smaller side length multiplied by 2 was your larger side length. So 3 times 2 is 6, 5 times 2 is 10. Okay, good. What else do you notice?
And the radical split has 3 on the inside.
Alright, so it's whatever that smaller number was times radical 3, whatever that smaller number was times radical 3.
And the smaller number also happens to be the outside of your radical.
It is. Anything else? So their angles are the same. We have a 30, 60, 90 for both. All right. So we noticed 2 patterns. We noticed that one with the 45, 45, 90 that had the same 2 sides, and the one side of that was like multiplied by radical 2. And then we had this one. We had a number multiplied by 2, and then that same number multiplied by radical 3 with this 30, 60, 90. So these are our 2 types of special right triangles. There are these special patterns that happen from similar triangles. So anytime you have a triangle that has 45, 45, 90 degrees, or 30, 60, 90 degrees, these special types of triangles happen. And you get a special formula that works for each of those side lengths. And so if you memorize these patterns, if you just know one piece of that triangle, you can solve for everything else in the triangle. So don't have to use Pythagorean theorem, don't have to simplify any radicals, anything like that. As soon as you know what one side is, you can know what those other 2 sides are. So it's very helpful to know these patterns. So this is something you'll want to memorize. So our first one is a 45, 45, 90 triangle. And so with the 45, 45, 90, 2 of those sides of that triangle are going to be the same thing. Right now I just have x as that random variable, whatever those side lengths are. We've had 5 for one of them, we got 7 for another. So 2 of them are going to be the same. That missing, or that other hypotenuse, the longest side of that triangle, it's going to be whatever that number is times radical 2. So we saw 5, 5, 5 radical 2. We saw 7, 7, 7 radical 2 for our second example. And so anytime you see the 45, 45, 90 triangle, if you know what one of these sides are, you know the other leg is going to be the same. And that longest side of your triangle, opposite of your 90 degrees, is always going to be whatever that number is times radical 2. We have a little mnemonic device for this. It's called, we go boo, boo, boo root 2.
Whoa.
So with that boo word, it's just representing a variable. So we had 5, 5, 5 radical 2. So the boo number is at 5. As soon as you know what that boo is, you can solve for all those missing sides. So it's 5, 5, 5 root 2. That's a boo, boo, boo root 2. It's a mnemonic device that's confusing for you. Don't worry about it. It's not something you have to know. It is fun. It's a little after Halloween though, so it's a little late. All right, our second pattern, our second special right triangle we have. This is our 30, 60, 90 triangle. So 30 degrees, 60 degrees, 90 degrees. So a 30, 60, 90 triangle, your shortest side, opposite of your 30 degrees, that is going to be your x. That's the number that's going to keep showing up as that pattern number. Whatever that boo number was on the last one, x is going to be that number, or that small side is going to be the number for this one. So your hypotenuse of your 30, 60, 90, it's always twice that value. So if x is 5, your hypotenuse is 10. If x is 3, your hypotenuse is 6. Your longer leg, opposite of the 60 degrees, that's going to be your x radical 3. So we had 3 was our smaller side, so that made this 3 radical 3. 5 was our smaller side, so that made us 5 radical 3. That works for whatever number you throw in. 20 radical 3. So you're always doubling for the length, or doubling for the hypotenuse, and multiplying by radical 3 for that smaller side. Our mnemonic device we can use for this one is tree, 2 tree, tree root 3. So it's whatever that number is your tree, 2 times whatever that number is, 2 tree, and then tree times root 3 is your last side. So tree, 2 tree, tree root 3. Once again, these are just quick mnemonic devices. They might work for you, they might not. Show you how you see them. So these are our 2 special right triangles. You want to be able to memorize these. You want to be able to memorize these patterns. Because as soon as you can memorize those patterns, these problems become very simple. You just look at it, know the pattern. Oh, I know these 2 sides. As soon as I find that boo number, as soon as I find that tree number, I can fill in those other 2 values automatically. You just multiply by 2, or multiply by radical 3, or use the same number, or multiply by radical 2. Whatever, just determine what triangle you have, figure out that number, and then the rest is simple. But you need to know those patterns. So let's see some examples. So I have this first triangle. First thing you need to figure out, is it a 45, 45, 90, or is it a 36? Alex?
There's a 45 degrees, so it's 45, 45.
45, 45, 90. As soon as I know what one of those degrees are, and as soon as I know I have a 90 degrees, I know it's going to be a 45, 45, 90. Because I can do 180 minus 45 minus 90, it's just going to give me 45 every time. So as soon as I know what one of those degrees are in 90 degrees, I should be able to figure out what that is. So 45, 45, 90, that's the boo root 2. So I need to figure out what that boo number is in my problem. 5. So it goes boo root 2, and I'm done.
Oh, so that's just your answer, you wouldn't do anything?
Yep, I'm just solving for those missing sides of my triangle.
Okay.
And I don't need to do any math as soon as I figure out what that number is.
Is that literally what it is, if that's it?
Yeah, if you get those triangles, if you memorize those triangles, it's just using that pattern every time. Just filling in those missing sides. So, looking at the second one, what type of triangle is this?
30, 60, 90.
30, 60, 90. So we need to think, what is that side, what is that tree for our tree, 2 tree, tree root 3, 4 for our triangle? It's going to be 4. It's always that smaller side, the opposite of the 30 degrees. So it's 4, so that's tree. 2 tree is 4 times 2. So what's our missing side?
4 radical 3.
4 radical 3. 3, 2 tree, tree root 3. Yep. Well, hopefully you'll be able to memorize some of that. And that's really all it is. Just using those patterns, just using those little mnemonic devices to help you find what that number is, and then use that to help find all your missing sides. So take a moment, see if you can do these 2. See if you can figure out what that number is, and figure out what those missing sides are based off of your triangles. All right, what do we find for our missing side of our first triangle? 16. How do you go about that?
Because the thing is 3, 2, 3. Yeah.
So we see our small, it's a 30, 69, so it's going to be a tree, 2 tree, tree root 3. Our smallest side is 8, so that's going to be our tree number. So tree, 2 tree, tree root 3, so 2 times 8 needs to be 16. Good. What about for the second one?
3.
3 were your missing sides? So it's a 45, 45, 90, so we know it's going to be boo root 2. If we're given that longest side of the hypotenuse, which is boo root 2, that means 3 is our boo. So our other 2 sides need to be 3. Good job. Let's try another problem, or another set of examples. So see, you have a little bit less information on these ones. See if you can still find those missing side lines. So what did we find for the first one?
4 radical 3.
Okay, so 4 radical 3. Sorry. How do you know that?
Small leg is half of your hypotenuse. Your
So-
larger leg is your radical 3.
It's a 30, 60, 90. So we know that hypotenuse is always twice of our smallest leg. So we can take 8, cut it in half, and that gives us 4. Our longer leg needs to be whatever that number is times radical 3, so 4 radical 3. Awesome. What about the second one? 17, 34. They gave us 17 radical 3, which is that tree root 3. So we know the tree number is going to be 17. So that makes our smallest side 17. Again, that's opposite of the 30. And then the hypotenuse needs to be 2 times 17, which is Awesome. So we're going to talk about one other thing, and we're going to talk about how it relates into our problem and ask for. So we have this thing in math where sometimes you end up with radicals in the denominator of a fraction. So sometimes you get radicals in the bottom of a fraction. That in math is bad math notation. It's like misspelling a word or not capitalizing a name or something like that. It's just bad writing. You don't want to do it. And so when we encounter denominators in the, or when we encounter radicals, I'm sorry, I can talk, I promise. When we can encounter radicals in the denominator, we need to do what's called rationalize the denominator. We need to get it out of that denominator. So we want to move that denominator, we want to move that radical out of the denominator. The thing is, we don't want to change the number. We want to make sure that number stays the same. So the way we go about this is we multiply the top and bottom by that radical. And the reason we're able to do this, and it's not changing the number, is if you think radical 2 divided by radical 2, what's any number divided by itself?
1.
1. If you multiply a number by 1, does it change? No. So we're really multiplying this answer by a funny version of 1, or like a really fancy version of 1. And so we're keeping the same number, but we're changing it. We're making it change or making it look different. So 10 times, or with multiplying fractions, we multiply straight across. So top by top, bottom by bottom. So 10 times radical 2, that's going to leave us with 10 radical 2. And we have to think, what is radical 2 times radical 2? What was that? So with radicals, you can multiply the inside. So it could be radical 4. What's the square root of 4? 2. So anytime you multiply a radical by itself, it's always just a number that's left over on the inside. Because if you think about it, radical 2 times radical 2 is the same as radical 2 squared, which is square root and a square cancel each other out, so you're just left with a number on the inside. Can we simplify this? What's 10 divided by 2? 5. And that would be your simplified version of what we started with. It's still the same number. If you put them in the calculator, they'll get you the same thing. It's just a better way of writing. It's fine.
What if you did 2 divided by 10, which gives you 5, put the 5 on the outside, and maybe 2. And then for the next one, what if you did divided by 3, 5, radical 3? Well, I don't really answer the next one, but I'm just saying. Is that like a pattern?
There is that. Yeah, you're on
Or
track.
yeah.
So if we were to do this one, if we were to show the work, it would be radical 3 times, or radical 3 over radical 3 is what you would multiply by.
I thought it was going to be something like that.
We get 15 radical 3 over 3. 15 divided by 3 is 5. We get 5 radical 3.
When do we ever see these? I've never seen this before.
We'll show an example.
Okay.
And they come in with special rights.
I've seen one of the three. I just said,
All right, so the pattern that we're going to solve is if you have a number, let's say 7 over radical 3, what you can do is you can automatically just turn that into your numerator, my numerator of 7, if I can write 7 and not 2, times whatever your radical is over whatever that bottom, whatever your radical is, just without that bottom. So you can just rewrite it automatically. That's exactly the same thing we're doing right here. Sometimes this will simplify, sometimes it won't. If it doesn't simplify, that's fine, just leave it as is. If it does simplify, try to simplify farther. But that's really all you need to do with rationalizing the denominator. Just move that radical to the numerator and leave whatever that number was at the bottom, leave that there. And so, when are we going to encounter these? So sometimes they come in with special right triangles. So what type of special right triangle do we have here? 45, 45, 9. So that makes it a boo, boo, boo root 2. Now which side did they give us?
the long one.
The longest. So what is that? Is that my boo or my boo root 2?
We were two.
Boo root 2. So 6 equals boo Henry. What's going on?
Whoa, it's going away.
There we go, there we go.
Okay. Oh, okay, of course. Like 60 times over. Alright, so that's my boo root 2. But based off of just 6, I don't know what that x is, do I? Because it doesn't have that root 2 in there. Could I solve for x? Because I need to figure out what x is to figure out what these two sides are, right?
Could you do the inverse operation at squared?
So to inverse this, I would have to square my x as well, which
Divide it.
it would get rid of the square root of the 2, but it's not necessarily the best strategy. It might work, but it would probably take some extra steps there. But these are being multiplied, so like Amanda said, we can divide by radical 2 to get rid of that. But if I divide by radical 2, now I have a radical in my denominator, which we know we can rationalize just by quickly
3 radical 2.
moving 6 radical 2 over 2, sorry. And then as Amanda said, simplifies to, if I can honestly write today, 3 radical 2.
Your brain really fast. Smart.
And so that was our x that we saw earlier, which equals 3 radical 2. So sometimes it's not always that hypotenuse that is the ugly number. Sometimes the shorter sides are. And so if they ever give you the number that has a radical in it, the tree root 3 or the boo root 2, and they give it as an integer, you need to solve for that number by dividing by that radical, rationalizing your denominator, and then throwing that in there.
So your two sides are bigger radical 2.
Yes.
Okay.
And that is where we're going to stop for today. We're going to continue to practice this tomorrow. Don't let those patterns slip away. We'll want to remember those for tomorrow and for Friday especially.